Okay, in this video I'm going to be talking about integrating to find volume using washers. So these will be some solids that are, hollow in some sense, or not completely solid all the way through. And so this is the second of 3 videos on volume. The first one I've got for you is we're going to take the region between y equals x squared and y equals square root x, rotate it around the x-axis. Okay, so this is going to make some sort of it's going to kind of look like a bowl, except the inside of it's going to be really convex and be like a cereal bowl that would really not be good to eat out of. So what we're going to do is we're going to, just like before, we're going to draw some representative rectangles. Okay, what are we rotating? And maybe even I will attempt to draw you one of the kind of cross sections of this thing after we've rotated it. All right, there you go. It looks decent enough. And so one of the cross sections of this thing is going to be, it's going to look like a washer. And so what we need to remember is that the area of an annulus, which, is basically the two-dimensional plane figure that's kind of like a washer, is going to be area between these two circles. So the area we're going to find by taking the area of a large circle. So that's pi r squared, where r is the large one. And then we're going to subtract the area of the small circle, which is pi times the small r squared. All right. And in the case of where we're actually rotating a region around an axis to find a volume, that'll be, each radius will end up being a top minus bottom, or maybe a right minus left type thing. Okay. So we're going to start, I'm going to get rid of the picture of the washer. And I'm going to start drawing my radii. Okay, so I'm going to start with a large radius. The large radius goes from the axis of rotation all the way out to the edge of the figure, or the region, or the solid that you're going to generate. Okay, so that's going to be my large radius. And then the small radius is going to be this one. And so I'm going to actually describe what these are. So large radius is top minus bottom is square root of x minus 0. And you might be thinking, well, of course it's minus 0. It's just the height of the function. And yeah, but when we go and rotate around something that's not the x-axis, this is going to be really important that we're always considering top minus bottom when thinking about our radii. Okay, so the small radius is going to be x squared minus 0. Okay. I might as well mention that this intersection point is going to be x equals 1. That's where the square root of x is equal to x squared. And so I think we're pretty much ready to, integrate to find the volume. Well, we could say that if we gave this annulus here a little bit of, depth. Oh goodness, it's not a very good figure, but, do the best I can. That is a prism. Okay, it has an area of its face, and its height would be, in this case, delta x. And so it's going to be, if we're going to take the total volume, it's going to be the sum of all of these annuli. Okay, so I'm going to say that that is pi r squared minus small pi r squared multiplied by delta x. And then, of course, we know as the number of these washers goes towards infinity and the thickness of each washer goes towards 0, this is going to turn into an integral. And what I'm going to do is I'm going to factor out the pi from both terms. So it's going to be pi times the integral from 0 to 1 of large r squared minus small r squared dx. And then I'm pretty much ready to substitute in on large r and small r. And unfortunately for us, these are pretty simple things. So this is pi times the integral from 0 to 1. Large r squared would be square root x squared. Minus small r squared is x squared squared dx. Okay, so this is x minus x to the fourth dx. So this is, okay, 1/2 x squared minus 1/5 x to the fifth. When you plug in 1 and 0, that's what you're going to get, and that's a safe place to stop. In the interest of time, I'm going to try to do more examples rather than, be really explicit about the last steps of the integration. Now we're ready to rotate around something that's not just the x-axis, so the line y equals 0. Okay, now we're going to take this thing and we're going to rotate this region G around the line y equals -2. Okay, so the same thing. We're going to take the same strategy. We're going to draw the large radius, starting at the axis of rotation and reaching all the way to the edge of the region, or the edge of the solid that's going to be formed. And then I'm going to draw the small radius as well. The small radius goes from the axis of rotation to the near side of the region we're going to rotate. And now I'm going to write out, okay, so the large region, you're thinking top minus bottom. So the large region is equal to f of x, y equals f of x, minus y equals -2. But that actually makes sense because the height of the graph of f of x plus those extra 2 that were going below the x-axis. And then the small radius is going to be g of x minus -2, top minus bottom. Now I know that volume is going to be the integral of pi r squared minus pi times small r squared dx, because our representative rectangles are moving left and right along the x-axis. Okay? We're going to need x to range from 1 up to 6. That's the boundary of my region. And I've already defined large r and small r. I'm going to factor out the pi. And so I'm going to start with, large r's. Large r is f of x plus 2. And then small r is g of x plus 2. And that's as far as we're going to be able to take it because we don't know what f and g are. Oh, whoops, I forgot a square. There we go. But a lot of questions on the AP exam, they'll generally give you f and g, but it's set up but don't evaluate. So this is as far as you go. Right? So this is actually a pretty typical type question. It's set up the integral, don't evaluate it. The next one is one that you could find more questions about on your free response packet because this was 2010 AB number 4. Okay? And basically what the question asked, what one part of the question asked was rotate the region around y equals 7. I don't know if it was set up but don't evaluate. Okay, I'm just going to say, oh, I know what this is. This is y equals 2 times the square root of x. I think, right? That would make sense because if it goes to 4, yeah. And then this is just y equals 1, 2, 3, 4, 5, 6. So what I'm going to do is I'm going to draw in the axis of rotation. Bless you. That line, that horizontal line is at y equals 6. The axis we're going to rotate around is y equals 7. Okay? Had we rotated this around the line y equals 6, it would have been a disk problem. And it would have been a little easier, but not too different. So maybe I'll do that as well afterwards. Okay, so starting with this one is one where the region is below the axis. Okay, that's a little different, right? Okay. You still take the same strategy. You start at the axis of rotation. You reach all the way to the edge of the region. That's your large radius. That might not have been enough room. Okay. How about I write that the large radius is equal to, bless you, 2 square roots of x. Nope. Right? What's the problem? Yeah, top minus bottom, not bottom minus top. Okay. So 7 minus 2 square root of x. Then the small radius is from here to here. That is 7 minus 6. Y equals 7 minus y equals 6. Okay, so that's just 1. And if you think about it, when we rotate this thing, it's going to look like, well, does anybody know what it looks like? Can anybody? It's something sideways. Yeah. Okay, it's a cone with a hole through it in terms of like, you know, I suppose maybe like a kind of a real thick ice cream cone. I was thinking it's a volcano turned on its side, right? Okay, yeah, maybe with time y'all will be able to visualize these things as well. All right, so keep practicing at home.
It does look like a
Yeah, I see that, but very thin, or like there's not room for any ice cream. Yeah. A very miserly ice cream seller would use that type of cone. All right, so I know that the volume is going to be the integral from, let's see, okay, again, my representative rectangles are going along the x-axis, so it's going to go from x equals 0 to x equals 9. You can count squares or set them equal to each other and solve. Of pi r squared minus pi r squared dx. Okay, and this is, I'm going to factor out the pi, 0 to 9. Large R is 7 minus 2 square root x. Small r is 1 squared. Actually, you know what? I'm going to take a step back, and I am going to write this as 7 minus 6. I almost like that better because it's more demonstrative of I know exactly what I'm doing. You know, I'm taking top minus bottom on both. But if you just see it as subtracting pi times 1 squared, integrated, it's just subtracting a cylinder, right? The tunnel that the lava comes up when there's an eruption. All right. All right, now, I don't have the free response packet with me, and I haven't looked at the 2010 free response questions for a while. But I expect that this one, since it was number 4, it's no calculator, I expect it was set up but don't evaluate. But, you know, if we wanted to evaluate it, the fastest way is going to be to use a calculator. So I'm going to do that. Okay, so I'm going to do pi times the integral, I'm going to use Math 9, from 0 to 9 of large R is 7 minus 2 times the square root of x. Okay. Oh, whoops. And we are squaring that. Minus 7 minus 6 squared dx. Okay, question from the front was, what happens, you know, these integrals that we need to take with respect to y, we go to do the calculator, what should I do there? Well, as long as you have not entered into y1, you could use alpha and type in y and put in terms of y and do dy. Or you could just not and just use x, right? But it's the same thing, right? If you just change the letter, you can think about all those steps of integration. Nothing's going to change based on which letter you use. So I recommend just using x always on the calculator. But if you really feel, if you're going to call on y1, then you have to use x because y1 is expecting x's, right? And because you've typed in y1 equals some function of x. But if it's just some regular old-fashioned integral in terms of y, we'll think about the example that I did at the beginning of class and then the one that y'all did on the quiz. They were the same, right? One was an integral in terms of x, one was an integral in terms of y. So you really don't need to worry about it too much, is what I'm saying. All right, and then I've calculated this, and I've gotten 282.743. All right, here we've got another thing that's going to end up looking like a volcano, and we're going to find the volume of the solid formed by rotating region N, which is enclosed by the coordinate axes y equals x to the third and x equals 2, around the vertical line x equals 5. So maybe I'll just actually draw in this, maybe that's 5. 1, through and draw a little axis of rotation. And, okay, same strategy. Draw the large radius. I don't like that placement. Whoops. Oh, wow. Lost part of my axis. And then my small radius will be over here. Okay, the large radius is going to be, okay, x equals 5, right, minus left. X equals 5, whoops, minus x equals, oh, well, I don't have that in terms of y quite yet. So I need to solve for the inverse function by solving for x, and I'll do that by taking the cube root of both sides. And I see I'm outside of my window. There we go, much better. And I'm saying that's x equals the cubed root of y. And so 5 minus the third root of y. Okay? And then the small radius is going to be x equals 5 minus x equals 2. So volume is going to be equal to the integral from y equals 0 to y equals, well, I would say 8 is where these things are going to run into each other, right? Because 2 to the third is 8. Of pi r squared minus pi small r squared, bless you, dy. And then that's going to be, I'm going to factor out the pi, 0 to 8. Large r was 5 minus third root y. Oh, hold on. Large r squared minus small r squared is 5 minus 2 is 3. Oops. Dy. Okay, let's just presume this is another setup, but don't evaluate. Because I do, at this point, I'm trusting that y'all know, okay, if you were to do this one by hand, you would have to expand this binomial. Okay, so it would be 25 minus 10 cube roots of y plus y to the 2/3 power. And then minus 9 in the integrand. I'm pretty sure y'all could then do the power rule, plug in top, plug in bottom, get a really nasty number, and be happy, yeah. But actually, it wouldn't be that nasty because you'd end up needing, okay, you'd have y to the 2/3 power that would bump up to the 5/3 power, and that's something you can take with 8. 8 to the 5/3 is, well, if we think about it, the cube root of 8 is 2 to the 5th, which is 32. Yes. Okay. Okay, now I'm going to change this question to, say, rotate this thing around the y-axis. It's another vertical axis we're going to rotate around, but this time it'll be a little different. Okay, so I'll start with the large radius over here. And in this case, this is going to be, you know, right minus left. X equals 2 minus x equals 0. And then the small radius will be here. Right minus left is x equals the third root of y minus x equals 0. Okay. Then when I go to take the volume, I know that it's going to be, volume is the integral of pi r squared minus pi r squared. Okay, we're adding up and down, so it's going to need to be with respect to y. And this is going to, just like the other one, run from 0 to 8. Okay. And then I'm going to substitute on my radiuses and factor out the pi, 0 to 8 of r squared is, large r squared is going to be 4, right? Because we take 2 minus 0, we square that, that's 4. Minus small r squared is going to be the third root of y squared. So that's y to the 2/3. And this is one maybe I will carry out the rest of the steps because it looks real friendly and it won't take that long. So this is going to be pi times, find an antiderivative, that'll be 4y minus, okay, I'm going to bump up the power by 1, so that'll be adding 3/3, and then multiplying by 3/5. and letting that run from 0 to 8. So this is going to be pi times one of these, bless you. Okay, so 4 times 8 is 32, minus 3/5 of, well, we had just talked about how 8 to the 5/3 is 32. Okay. Minus, when I plug in 0, I'm just going to get 0, so just power supply. And that's an acceptable answer. Or you could say it is 2/5 of 32 multiplied by pi, or 62 pi over 5, 64 pi over 5, right? See, why even risk it? Just stop there. All right, and then the last example I'm going to do on this one is actually going to be a disk problem again, just to remind y'all that not all of these need washers. Okay, rotating n around the line, x equals 2. Well, that's all of a sudden this is going to become the axis of rotation, and so I don't really need a large radius and a small radius. I just need one radius. And that's going to be right minus left is going to be x equals 2 minus x equals the third root of y. There is no small radius, so I'll just get rid of that. And when you're adding disks, it's the integral of just pi r squared dy from 0 to 8. So this is pi times the integral from 0 to 8 of r squared is going to be 2 minus the third root of y squared dy. And this is the type of integral that if you were needing practice on your integrals or practice with your algebra, it would be a good one for you to do. But I'm not going to be doing it on this video. And on second thought, I think I've covered pretty much all the cases for volume using the washer technique that I'm going to need for this video.